The article Fundamentals of the Mechanics of Continua appeared in the Encyclopedia of Mathematical Sciences in 1914. This project about the encyclopedia was an enormous project who aimed to gather all mathematical knowledge at that time and also to include the applications of mathematics into these books. This was rather important for one of the main supporters and one of the editors, Felix Klein, that also applications are included in this encyclopedia. And this is, for this reason, there are 4 books just about mechanics. And it were these 4 books I found during my PhD in the old glass cabinet between the old books, and it was also the article by Hellinger who attracted my attention. As a student, I was educated in dynamics in a Lagrangian sense, so with variational principles, but my education in nonlinear continuum mechanics was more in a Trustallian way, so everything started from balance of linear and angular momentum, and it was certainly non-variational. And the article of Hellinger was in fact my first contact with the variational formulation of continuum mechanics. But at that time, in my second year of my PhD, I did not realize how important this work was. And you just have to look at literature. You find a vast amount of books in nonlinear continuum mechanics following Trustal, and there is one single book, one single textbook which treats continuum mechanics variationally. This is the book of Salençon. Maybe the one of Charmat a little bit before, but this is just in French, so there is one English book which takes the principle of virtual power as its basics for treating continuum mechanics. So it took me another 5 years until I met Francesco Dell'Isola at the conference in Calgary, and he asked me if I know this article, and he told me, yes, certainly I do, and he asked me if I can translate it into English, because so far there is no translation into another language. It's just written in the original German style. I have to be honest, I completely underestimated the translation of 90 pages of a 100 years old mechanic books. And if the book or if the article was not that good, I would have stopped after 10 pages. But every page you turn, you realize that 100 years ago, they knew so much. It would be, still today, it would be an awesome book. But let us first talk about Ernst Hellinger. Ernst Hellinger was born in Striegau, this was formerly Germany, and he studied mathematics in Heidelberg, Breslau, and Göttingen, and presented his doctoral thesis to David Hilbert. After being an assistant of David Hilbert, he got a position as Privatdozent at the University of Marburg, and this was exactly the time when he wrote the article for the encyclopedia. In 1914, he was appointed full professor in mathematics at the newly opened University of Frankfurt. And for 20 years, being a successful scientist, researcher, and teacher, he was, under the Nazi regime, removed as a professor since he was a Jewish scientist. 3 years later, it became even worse. During the Kristallnacht, he was arrested and deported to Dachau. And just due to the effort of his sister, Hannah Meissner, who already lived in the United States at that time, she could manage with friends together that he got a position as lecturer at the Northwestern University in Evanston, and he got out he was discharged from Dachau after 6 weeks. So the last 10, 11 years he spent in the United States and died of cancer in the age of 66. So rather young. But let us delve now into the work of Hellinger. The work of Hellinger is structured in Lagrangian schemes. So in the introduction, he starts with arguing and explaining why variational principles are that important for physics and mechanics. Then in the notion of a continuum, he introduced kinematics of various continua, and what follows after kinematics, that's statics and kinetics, which is a rather old-fashioned word of what we call nowadays dynamics. And since he doesn't bother about what causes its forces in the first two sections, he has a rather big section about constitutive laws, where he treats such things as potential-based approaches, theory of elasticity, ideal fluids, capillarity, thermoelasticity, and in the end he even goes to the theory of relativity. So it's really astonishing. In his introduction, Hellinger claims that variational principles are the best tool to formulate physical theory in a mathematical unifying way. And pay attention, with variational principles, Hellinger does not mean variational problems which aim to find extrema for a given functional. No, he means that a variational principle should be formulated in the form of the necessary criterion of a variational problem. So the principle should be of the form that you have a definite integral of a linear form, however it looks like, and this should vanish identically for all delta x and further introduce kinematical quantities. For us, the introduction of the kinematics of the three-dimensional continuum looks rather familiar. He makes two assumptions. The one is that material particles are distinguishable, which means nothing else that we have an existence of a reference configuration, which he parameterized by 3 Cartesian coordinates A, B, and C. And the second assumption is the assumption that the body occupies the space continuously, which he gets by 3 deformation functions, which has to be smooth. So every system of functions describes entirely a certain state of deformation of the continuum, so which implies that the configuration manifold is certainly infinite dimensional. And as he goes on, in a Lagrangian sense, somehow you have to get the tangent space, this infinite dimensional configuration manifold. And Hellinger uses for that tools from calculus as variations, and introduces a variational family of the placement functions which are smooth in the parameter sigma, and for sigma equals 0, the variational family coincides with the actual configuration of the body. So by taking the variation, which means nothing else than taking the derivative with respect to the parameter sigma and evaluate it at 0, we will get a vector field over the current configuration of our body, which is nothing else than the tangent vector to this infinite dimensional configuration manifold. It was also possible when to to go back to the more classical interpretation of an infinitesimal virtual displacement. So when the parameter sigma is small enough, you can think of this where we have the current configuration and sigma times the vector field. We got a slightly changed configuration, which is then called the infinitesimal virtual displacement. So proceeding in the Lagrangian scheme, and he introduces the notion of work or the notion of force in the sense of D'Alembert, and here it is the easiest, just to let Hellinger speak. He says that the collection of forces and stresses of any kind have in common that for any virtual displacement they expend a virtual work, delta A. So not forces are his primitive quantities, but the virtual work is his primitive quantity, which he bases mechanics on. Furthermore, he assumes that, or he specifies further that the virtual work has to be a linear and homogeneous function on the virtual displacements, and that the virtual work is independent of the choice of coordinates. Hellinger suggests a first version of the virtual work for a continuum, and he is completely aware that this is not complete at all. I mean, you can just add linear forms evaluated at certain points and add this to the virtual work, or you can also add some virtual work terms defined on a surface or on lines within the body. When we look at the terms, it becomes clear that we have here forces per unit volumes, and on the boundary of the bodies we have forces per unit area. What we find here, which we define as the stress components, which are the quantities being defined as the duals to the gradient of the virtual displacement, there is no interpretation yet what's the meaning of these components. But also, for this, Hellinger answers promptly. Then, since the stress components are smooth or continuous, at least continuous, you can, of this second part of the virtual work of the stress components, you can take the partial derivative. And taking the partial derivative on an arbitrary subset of our body, we will obtain the stress state. You can read this here actually, that the stress state in V1 expands the same virtual work. That means it acts equally as if besides the volume forces in 1, these are the volume forces, the force per area xn, these are these forces per area, was acting on the surface element ds of S1. So without arguing with a tetrahedron theorem, he made the connection between the stress vectors acting between the subsystem within the body and the normal vector, which defines the thought cross the section, cutting section through our body. And by specifying the normal vector, we immediately see that the components of the stresses are force per unit area. And as Lagrange calls this principle of virtual velocities, also Hellinger stresses out the importance of the kinematics and calls his principle of virtual displacement. Nowadays, we call it principle of virtual work or virtual power, whatever literature you look like. And this is not a version from Paul Germain from the 1970s. It is really the version of Hellinger written in 1913. And it's rather astonishing because it's exactly the same. What he writes is that a continuous medium in a particular state of deformation for certain volume and surface forces and for a certain stress state is in equilibrium if and only if the total virtual work of these forces and stresses vanish for every virtual displacement which is admissible with respect to the possibly imposed constraints of the continuum. Making the standard arguments, so taking the partial derivatives of this term here, using the lemma of calculus of variations, we obtain the local equilibrium equations, and on the boundary we get the boundary conditions. So in a variational formulation we have for free the boundary conditions. They are already included in the basic formulation. This sounded really reasonable for me as a student, so I thought, okay, that sounds good. It seems that is a good axiomatic scheme. But the only next time I have found citation of Hellinger was in the work of Troussel and Toupin in the classical field theories, and Troussel claimed that the derivation given by Hellinger failed through petitio principii, since the stress components appear in the original variational principle. Furthermore, he specifies that no variational principle has ever been shown to yield Cauchy's fundamental theorem in its basic sense, as asserting that existence of the stress vector implies the existence of the stress tensor. Is this allegation really substantial? We have to bear in mind that Troussel has a completely different axiomatic scheme in mind. Then Troussel was a follower of a non-variational formulation of continuum mechanics. So the formulation of continuum mechanics, which was basically achieved by Euler, Cauchy, and also Kirchhoff. Cauchy made the assumption that the forces are composed by volume and surface forces only. Furthermore, he restricts the interaction between subbodies to take place exclusively by contact interactions. Then you can take the integral balance laws, which are basically formulated by Euler, and you can show in the famous tetrahedron theorem how the normals are related to the stress vectors, and there the stress tensor as a second order tensor do appear. And putting these results into the integral balance laws, we get by localization the local equilibrium equations and the symmetry of stress. In contrast to the non-variational continuum mechanics, Hellinger hasn't done any assumption about contact interactions between subbodies. Then in a variational formulation of continuum mechanics, the contact interaction is not an assumed but a derived concept. So, and the derivation, how the contact interaction takes place, is done by, when it's possible, by integration by parts. So the allegation of Troussel was not at all substantial. It was just these two theories, non-variation and the variational formulation, they start at different points and they meet in between. So for the classical continuum, it's no problem that you end up with the same equations and you will describe the same physical phenomena. In order to calm the hardest critics, Hellinger also bridges to non-variational formulation. And how he has done this, since the virtual work has to vanish for all virtual displacements, why not choosing a virtual displacement which is constant on an arbitrary subset, but zero outside? The problem is such a virtual displacement field would be discontinuous, and we started with the assumption that everything has to be smooth enough. but also this problem has been solved by Hellinger, then what you can do is he approximate these virtual displacement functions by a family of virtual displacements by putting around the volume a small volume V1, which is arbitrarily small, and in which the constant virtual displacements decrease to 0. When using this virtual displacement field, they are constant on V1, so the virtual work contribution of the stress will drop out, and the virtual work contribution of this volume V2 can be integrated by parts. So we will have on S1, we will have a contribution of the virtual work, and we will have this volume force within V2. In the limit process, this will vanish because all the forces are bounded and V2 becomes arbitrarily small. So the only way that the principle of virtual work can hold is that this integral here has to vanish. And this is nothing else but the equilibrium of forces in an integral form. You can do this in a pretty equivalent way by assuming that we have a virtual rotation. And with the same arguments, you get out with these equations here. And here we have the two components of the stress. And if the stress is symmetric, this would vanish, and it will lead to the equilibrium of moments. What comes now is very astonishing. Then Hellinger argues that by postulating the law of equal areas in the usual form, the symmetry of the stress dyad follows immediately. So the first time he doesn't use a variational principle to induce a result, he uses a non-variational form in order to show that the stress dyad is symmetric. In a footnote, he remarked that you can also assume from the beginning that the stress has to be symmetric, which is in German literature known as the Boltzmann Axiom. I don't know actually why it should be the Boltzmann Axiom, but Hamel called it in 1908 Boltzmann Axiom, but I could never find it in the works of Boltzmann that he has ever told something like this. It's just at one point he says something, the stuff about the symmetry of the stress, this is difficult. This is the only thing Boltzmann mentions. But what was missing actually to Hellinger, in order to argue here in a variational form with variational arguments, is the axiom of power of internal forces, which has been formulated 60 years later by Paul Germain, and which asks the virtual work of the internal forces to vanish for all the rigid virtual displacements. So this is actually nothing else but a weak form of the law of interaction. The work of Hellinger is not at all that astonishing just because he formulated classical continuum mechanics in a variational form. He went much further. So for Hellinger, it was the most obvious to add to the virtual work per unit volume a linear form of the 18-second derivatives of the virtual displacements. So he was already aware of second gradient theories 100 years ago. And he was also aware that, he also derived that this induces a surface tension which is necessary for describing capillarity. In the same, or in the book about physics, Minkowski wrote a whole article about capillarity where he used exactly these surface tensions. The same he has done with oriented media with oriented particles in the sense of the Kossler brothers. Not that he introduced an action as the Kossler brothers did, he introduced it with the virtual work. And the plan here is crystal clear again. You introduce new kinematics, you define your new linear form, which you can add to the virtual work, and then you postulate the principle of virtual displacements, and you get all your equations. So Hellinger can be counted clearly to these people who developed variational continuum mechanics after Lagrange, Piola, and after Hellinger, Germain. And in his work, he really pointed out how important the principle of virtual displacement is in order to get into new fields of mechanics. And often, it is not necessary to introduce new laws. It's just necessary to introduce a new kinematics and refine your model, and then you will get completely new phenomena in mechanics. So even though this work is now more than 100 years old, it is still very modern. So thank you very much for your attention.
Questions?
Just the last line. Is this the Lagrange D'Alembert principle that you write down? Is delta A equal to not zero, equal to something? The one that is not formulated by Hellinger.
Which one? This one?
Yeah, that one.
This one is the axiom of power of internal forces, that all the internal forces have, of a given subset, they have to vanish when you get a rigid virtual displacement on it. So when you look at, you can simplify it to 2 points, 2 material points with the interaction, and when you take the rigid virtual displacements, this will give you axio equals reaction in force direction, and also that they have to be in line. You can do the same for rigid bodies, where you have that when you cut a rigid body, then you have forces equals action equal reaction, and also the torques have to be equal but opposite.
Yeah. Just out of curiosity, compared to modern standards, how much rigorous is Hellinger concerning regularity assumptions for performing division by parts, for instance?
He assumes in the very beginning that everything is smooth enough. So, but he really states it.
He doesn't try to optimize the assumptions.
No, not at all.
I have a comment. Simon was politically correct, so he avoided useless polemical observations. It is stronger than me. It is stronger than me. I want to tell that we found in Hellinger paper a nice and elegant regularization argument based somehow on Unison lemma, which he imagines to be true. So he applies it without having a formal proof. So that it proves that if the principle of uniform work is valid for the whole body, then it is valid for every sub-body. Which is an argument rather trivial. He is presented in the 2016 and 14 and 10 literature. You find something like 50 papers of famous names in which they claim to have a non-standard formulation of the principle of Clifford, which Hellinger 100 years before proved to be implied by the standard. It's a pity that Lucio is not here, because he could write a note on this lost invention. No. So if there are no more questions, maybe we can go to our coffee. Okay, but